Welcome. Today, we're going to trace the incredible intellectual journey from a single abstract idea all the way to the physical blueprint that powers, well, pretty much every digital device you've ever used. It's a story that starts not with silicon and circuits, but with a thought experiment.
So it really all boils down to this question. How on earth did a purely mental exercise, a machine that existed only in logic and on paper, become the foundation for everything, from our laptops and phones to the supercomputers that are shaping our future? Well, to answer that, we have to go right back to the beginning, to the idea itself.
So, our story begins not in a lab full of wires and vacuum tubes, but inside the mind of one person, Alan Turing. And here's the thing. His contribution was entirely conceptual, but it was so powerful that it basically set the absolute boundaries for what computing could ever hope to be. Now, the key word here is theoretical. The universal Turing machine wasn't a real device you could build. It was an abstract idea. Think of an infinitely long piece of tape, a little machine that could read and write symbols on it, and a simple set of rules. That's it. But what Turing proved was that this incredibly simple model could, in principle, do any calculation that any other computer could possibly do. That concept, universality, is the absolute bedrock of computer science. So, and this is the crucial point. This was not a blueprint for building a computer. It was a mathematical tool, a way to understand the fundamental limits of computation. It answered the question of what is computable, but it left a giant practical question wide open. How do you actually build a machine to do all this efficiently? As it turns out, the answer would come from the extreme pressures of history. Right. So the Second World War created this just unprecedented demand for high-speed calculation. We're talking about everything from cracking enemy codes to calculating artillery trajectories. This pressure cooker of innovation forced the leap from abstract theory to actual functioning hardware. And machines like the famous ENIAC were absolute marvels for their time. But they had this one massive problem. If you wanted to change the computer's task, say from one physics problem to another, technicians had to spend days, sometimes weeks, physically unplugging and replugging hundreds of cables and flipping switches. Programming wasn't code. It was a physical, exhausting act. This was a huge bottleneck, and they desperately needed a better way. And this brings us to the second giant in our story, John von Neumann. He was consulting on the successor to ENIAC, a machine called EDVAC, and it was there that he put together the solution that would define the modern computer as we know it. And here it is. This is the core of his idea, and it's so elegant. He thought, instead of wiring the program into the hardware, why not just store the program, the instructions themselves, in the computer's memory, right next to the data it's working on? This was the game changer. All of a sudden, you could reprogram a computer in an instant. Just by loading a new set of instructions into its memory, the hardware could stay exactly the same. So von Neumann laid all this out in a famous report, describing 5 logical parts. First, you've got input. Think of a keyboard to get information in. Then you have memory, which is crucial because it holds both the program and the data. The heart of the whole thing is the processor, which he split into 2 parts, the central arithmetic unit, which does all the math, and the central control unit. Think of that as the conductor of an orchestra. It fetches the instructions from memory and directs the whole show. And finally, you've got output, like a screen, to show you the results. This basic structure, it's still the foundation of almost every computer built today. But believe it or not, this practical blueprint was just one piece of von Neumann's incredible intellect. His thinking about systems, logic, and strategy wasn't just limited to computer architecture. It ranged across a mind-boggling number of fields. For instance, that same focus on logical systems led him to co-create game theory, the mathematical framework for analyzing strategic decisions that is absolutely central to economics and AI today. And he didn't stop there. He also applied this kind of thinking to biology. He theorized about what he called self-reproducing automata, basically machines that could replicate themselves and evolve, which offered a logical basis for how complexity could arise in any system, living or not. And way, way before it was common, he was fascinated by the ultimate complex system, the human brain. He spent a lot of time exploring the deep differences between a computer's step-by-step, one-thing-at-a-time processing and the brain's massively parallel network. That's a challenge that still drives AI research to this day.
Okay, so let's bring these 2 incredible threads together. On one hand, we have Turing's abstract idea defining what is even possible to compute. And on the other, we have von Neumann's practical blueprint for how to actually build a machine to do it. This, of course, raises a really important question. How connected were these two ideas really? This is such a fascinating historical question. I mean, did von Neumann just independently come up with the design that happened to be a universal computer? Or was he consciously building on the theoretical foundation that Turing had already laid down years earlier?
Well, the evidence is pretty clear. This quote here confirms that von Neumann was definitely familiar with Turing's revolutionary paper from his time at Princeton. And you can see the connection. The logical parts map directly onto each other. Von Neumann's memory acts just like Turing's tape, and the processor acts like the read-write head. There's a direct intellectual lineage there.
And this really is the ultimate takeaway. These two contributions are totally distinct, but they're also perfectly complementary. Turing gave us the profound, abstract theory of what universal computation even is, defining its ultimate power and its limits. And then von Neumann gave us the elegant, practical architecture to actually build it. It's this partnership, this blend of pure theory and brilliant engineering that created the digital world we all live in today. And it's amazing to think that nearly 80 years later, we are still living in the house that von Neumann built, on the foundation that Turing discovered.